Good evening, everyone. Welcome. Good evening. Thank you very much for joining us. I'm just waiting for our attendees to get to a decent level before I hand over to Frank. Okay, we are still going.
Yeah, most people are not exactly to the point. I think neither me actually.
But okay, we seem to be steady at about 95 at the moment. So welcome, everyone. It is a great pleasure to have you all here this evening. I would like to thank our education partner, Hoya, for arranging this wonderful webinar with us. And a thank you to Frank, who has agreed to join us and give us some of his wisdom that we know we are all waiting to learn from. Just so that you know, this webinar is recorded and it will be in our Academy's membership area for those who are members who want to then re-listen to the lecture, because as we had a discussion earlier with Frank, that people do need to go and have a look at it again so that we can reflect, learn, and relearn if we've forgotten some of the important points that are being discussed. It is my great pleasure, Frank, to invite you and please go ahead with your presentation.
Yeah, thank you for these nice and kind introductory words. And I would like to start right away just showing you the title slide. And I just would briefly like to make the point that most of the work was actually done in Basel at IOB, where I was working for 5.5 years. But I'm now back to Tübingen, where I came from, and still sit here in the office and give the talk. The picture you see behind my titles and everything is actually the most expensive hotel in Switzerland, which is in Basel. If you ever stay there, you know now it's sitting on the River Rhine. And if I look at it without my spectacles, that's what I see without spectacles is around it. So this is a refractive error of 4 diopters, so this is not so much fun. But now let me get started. I wanted to start with the old question, how precisely does the eye have to grow to make full use of the pixel density that we have in the fovea? And to do this, it's always important to realize that our photoreceptors cannot get thinner than about 2 micrometers. So this is the pixel size that you have. And if you would like to have high acuity, you need a reasonably big image to sample it enough with your pixels. And that's why vertebrate eyes generally are reasonably big. Ours are 24 millimeters. This is not infinitely big, but still quite big for an optical system that is built by nature. And now the important point is if you take a quarter diopter lens in front of your eye, you hardly see the difference in focus. And this means that this is about the depth of focus that you have to play around with without losing visual acuity. And if you convert this into axial length change, 1 millimeter longer eye makes about 2.7 diopters of myopia. Then you can see that a tenth of a millimeter is about the precision that the eye has to reach to make full use of your visual acuity by the sampling of the photoreceptors. And if the eye deviates from this perfect match between focal length and axial length, then each single pixel or point that is imaged on the retina will become a disc. And this is a little bit illustrated by the eye in the bottom. And on the right, you see a Christmas tree with a defocus of 3 diopters at a pupil size of 5 millimeters. And you can see that the candles become discs. Okay, is this purely genetic? I think I tell stuff that you may know, but I start this way anyway. Is this genetically possible? Probably not. The genes cannot generate such precise growth that you are down to a tenth of a millimeter in a length of an organ. So no organ in the body has this precision anyway. And this already suggests that you need some feedback control that aligns the length of the eye with the focal length. Nevertheless, it was still the common opinion among ophthalmologists and optometrists until about the mid 70s of the last century that eye growth is fully inherited, and myopia is one of these inherited problems where you have too much growth. So it was a big step forward that Wiesel and Raviola, the two guys you see on the left, they studied monkeys and closed their lids to study amblyopia. And as a side effect, they realized that these eyes became longer than the fellow eyes that were not covered. And important point here is now that this discovery tells first time that it's a visual control, basically, because the only thing that changed was vision. They did control experiments to show that it wasn't the lead suture by itself and stuff. It's also interesting that this is the only experimental paper in Nature that I am aware of on myopia. I mean, certainly there were reviews in Nature on myopia, but experimental paper, many people tried to get in with some experiments in Nature, but it didn't really work, interestingly. Now, if you degrade the image on the retina, you know all this maybe, the eye loses control of its growth, and what it does, it just grows longer. And this is called deprivation myopia, a very common thing that happens in all animals that were studied up to date. Interestingly, this deprivation myopia is not very predictable in each animal. So in one animal, you get a lot of myopia, which is shown on the right bottom in the blue graph. On the other animal, you get only little, and it's clear this is genetics. So the variability of deprivation myopia is really genetics, and you can find this out by comparing the left and the right eye, and they all get equally myopic, even though they grow open loop. They have no feedback in their growth. Now, deprivation myopia was first introduced by Josh Wallman, whom you see in the middle bottom, who first learned that just putting plastic goggles in front of chicken eyes gives you a lot of myopia. And this is, for many years, the most frequently used experimental paradigm. Now, what this paradigm showed, for instance, is that you induce myopia also when the optic nerve is cut, which means that the brain doesn't tell much about what eye growth should do. It's really happening in the eye. And Josh Wallman and his colleagues had a paper in Science in 1987 where they found that uh, it's really the retina that controls eye growth because you can cover half of the visual field as you see on the right, and then you get really growth only in the eye half that has a defocused or poor quality image. These are data from our lab on the right bottom. Now, there's more than deprivation myopia. The eye wouldn't survive only with the mechanism of deprivation myopia because there is no final set point. You know, it just grows and grows and nothing, it will never reach the optimal position. You can argue that when the eye gets close to emmetropia, then the deprivation reaches a minimum. And so it's kind of a possible mechanism, only the mechanism wouldn't work as soon as you have some kind of image recordation, it runs off and then you are done. And therefore, nature did much more than just putting deprivation myopia into the eye. And we started putting lenses on the chick, as you know, many years ago. That's now 40 years ago or so, even more. I don't know. Frightening, yeah. And then we found that depending on whether you focus the retina before the retina or behind, the eye fully realizes what the correct position is and grows more or less. I think this is all well known, and I shouldn't repeat too much about it. Only this is a closed loop mechanism because it really finds its set point and stays there. So this is a full mechanism of emmetropization, goes both way. It's a closed loop feedback system. Now, Josh Wallman's group and we also were certainly interested in finding out what is the mechanism then that inhibits eye growth. We know poor image makes it long, but there must be more. It must be something there that also makes it short or stops growing anyway, make it stop growing. And they did a clever experiment. They had a +7 diopter lens in chickens, but on top of this lens, they put different types of diffusers that degraded the image. So basically, they let the deprivation myopia run against the plus lens effect, which is inhibitory. And the striking thing was that even if you take a diffuser that cuts visual acuity down to 1/10, this is a 0.1 in the bottom Bangerter foil, the eye still realizes that it shouldn't grow longer and rather stays on the hyperopic side. And you can see the data in the top the eye still gets shorter. And at the end, this shows that you can degrade the image quite a bit before the mechanism doesn't realize anymore that it should inhibit eye growth. Interestingly, the two mechanisms, the one that let the eye grow longer and the one that inhibits eye growth, they are not the same. And there are so many arguments for that. I go to the left side here on this graph where you have an occluder in the top and a minus lens, both the things that make the eye long. And there you can see you can inhibit this mechanism, letting the eye grow by atropine, pyrazine, dopamine agonists, nitric oxide, bright light. You can inhibit it by stimulating the on channel in the retina, preferentially like with reading with inverted contrast and stuff, or flicker light. This all inhibits this mechanism that triggers more eye growth. But interestingly, the mechanism that inhibits eye growth, this doesn't care about atropine, pyrazine, dopamine, and it also isn't inhibited by the on stimulus. It's only if you give a chicken atropine, it no longer develops myopia with a diffuser. But if you give it a plus lens, this works just fine. And so basically what we can say, there are two arms of emmetropization as in any feedback loop, but they are genetically, biochemically, also stimulus depend completely different. So do we understand now why myopia develops? No, we don't. Because if there is this strong inhibitory pathway, myopia should really inhibit itself. You would expect this from a closed loop feedback system. If the image is now in front of the retina, I should immediately stop growing. And also undercorrection should inhibit myopia, which it doesn't, as you know. And none of the inventions that are known these days are inhibiting myopia completely. So you know we haven't fully understood what the mechanisms really are. And what we did then in Basel first is what stimuli does the retina really need to inhibit eye growth? We know poor image makes the eye grow more, but this is not it because obviously the eye growth can be inhibited, and we would like to know with which stimulus would do it. And so what we decided to do now is we wanted to present to the human retina two types of stimuli. One is a calculated defocused image, and the other is a real defocused image with a plus lens, and see whether the retina can distinguish these two cases. And what we did, we had subjects watching a movie at 2 meter distance, and these subjects could certainly focus easily at 2 meters, no problem. But then we gave them a +3 diopter lens, which you see in the top. And the far point then certainly moves close to 33 centimeters or so, which means the movie is now no longer in focus. So this is real defocus. But what we now could also do, we calculate the movie unsharp and give the subjects no lens so they can look at the screen, but it looks just as if they would be out of focus. Only the retina gets now additional information, which we don't know about what it exactly is. But in one case, it's real defocus, and the other, it's calculated defocus. And with a paradigm of just taking into account the defocus point spreads become a disk, you can nicely calculate what 2.5 diopters of calculated defocus would do to the movie. So I programmed this, and you can nicely run the movie now with artificial defocus, basically. These are the experiments again. In top, the people watched it in focus, and in the second case, they watched it with real defocus with a +3 diopter lens, which makes a 2.5 diopter defocus on 2 meters distance, or with a calculated defocus. And now we would like to know, what did the retina say in these cases? And what we can do here, we can wait 2 weeks and let people watch the movie for 2 weeks and see whether eye growth really has changed. But I think ethics would run against this. And so what we did instead, as many others do these days, we measured the short-term changes in eye length, which you can induce by these kind of stimuli. And these changes are showing up because the choroid, which is a heavily perfused layer behind the retina, gets thicker as soon as eye growth is inhibited. So we can just measure tiny changes in eye length showing the retina these two movies. And what we found is shown here. So the first bar or column on the left is the people looked at this movie in focus. You can see there are tiny or random changes in eye lengths, which are sometimes not so small, it's 10 micrometers or so. But basically, the average value stays at 0. So it's just more noise on the axial length, and there's no consistent change in any direction. But now, if you put a real plus lens in front of the eye, calculate, let's go to the middle thing, calculated defocus. What you can see now is all except of one eye, they all got longer and the choroid got thinner. And this is the same with in the emmetropic people, which are in green, and the red ones are the myopes. But now the most interesting result was actually with a real defocus of 2.5 diopters. In this case, we found that emmetropic people really got shorter eyes because the choroid thickened. And these are the green lines on the top. But the myopes, they didn't care. They also developed longer eyes, even though there was a real myopic defocus. And basically, what you can conclude here is that the myopic eye has lost the ability to recognize that there is positive defocus. Basically, the inhibitory arm of the mechanism is broken. And I think this was a new finding, and people, it slowly crawls through the scientific literature, but many people had doubts that this can be true, but I think at the end it will be true. Uh, I wanted also to add a small slide from last year. Certainly, it's interesting also to see what happens in hyperopia. A hyperopic eye doesn't care whether you give it a lens or not, it always stays hyperopic. This is different from myopia, which is very sensitive to any change in visual input. But if you are hyperop with +5 or something, like my colleague in Basel, who you can see in the middle bottom, Lea and Gracia, she's +6, and there is no change ever in her life in her refraction. This is typical for hyperops. Now the question is, are these hyperops no longer responding to the lenses? And interestingly, in the rightmost two bars, two graphs, you see the responses of the hyperops to the plus and minus lenses, and they respond just like the emmetropes, which are in the middle, the violet bars. The emmetropes have longer eyes with a minus lens and shorter eyes with a plus lens. So the hyperops have their problem not in the retina, it's a problem later on in the processing pathways to the sclera. That's what we can conclude from this, because they can fully respond to defocus, and the retina tells the choroid that it should get thicker or thinner. Yeah, and the myopes on the leftmost column, they respond completely erratic. Actually, in this study, they developed longer eyes with a plus lens, which makes no sense at all. Basically, it tells again that their mechanism is not responding correctly. Okay, so how does the retina recognize where the focus is? And this is a topic that is 40 years old. Nobody really got an extremely convincing explanation. And at the end, I think the most likely explanation is really the chromatic aberration. Different from our higher order monochromatic aberrations, which are extremely variable among different people, the chromatic aberration is very consistent, and everybody has about the same chromatic aberration. So the retina, if it would compare the focus in the red and in the blue, would get a very nice information about which way the eye growth should be changed. And therefore, we had the idea we offer to the eye simulated chromatic aberration. I show you in the next slide. But actually, I wanted to show this slide in between. Chromatic aberration is something that is inherent in all eyes. And it's interesting that nature even used it for very useful things, like for these jumping spiders when they catch food. On the bottom, you see a jumping spider who is fed on Drosophila. And this guy sits there, and at the end, it jumps and is perfectly precise and gets Drosophila all the time. But the question is, how can it measure how far the object is away? So the people, it was a science paper, put them in green light and found they are very good in green light, but in red light, if you look at it again, you can see on the bottom, on the top actually, of these four images, that then the jumping spider jumps too short in the red. And this because chromatic aberration is used for distance estimation. And this was a very nice experiment showing that chromatic aberration is also useful for feeding in spiders. Now, back to chromatic aberration in humans, the curve is shown on the right. You can see that we are about 1 diopter myopic in 450 nanometer blue and about zero point 0.3 or zero point 0.4 diopter hyperopic if we are focused to 570 on the green yellow or so. So this is a solid error or difference in refraction of about 1.3 or 1.4 diopters. It's based on the fact that optical materials all show chromatic aberration, which means the refractive index is dependent on wavelength. And this was already described and discovered by Snell 64 years before Johann Sebastian Bach. So quite impressive. It's known forever. Now, what can you do? You look at a computer screen. A computer screen has a red, green, and blue channel. And certainly you have a blue image, a green image, and a red image. And if they are put together, then you get these colored images that you can see in the movie. So it's quite easy now to, for instance, low pass or calculate the blue image only unsharp and leave the red image sharp. Or you do it the other way around. You calculate the red image unsharp and leave the blue sharp. And what is happening then, or what would you expect? I have it in the two boxes in the top here. If blue is in focus, this means the eye is too short, and the retina should tell the eye that it should grow more. If red is in focus, it would tell the eye that it is too long, and then it should be inhibited and become shorter. So what we did, we focused, we filtered these movies, James Bond, as you see, um, either the blue channel sharp or the red channel sharp. And the prediction is in the top. We will see whether it happens. And actually, exactly this happened. So if the 20 subjects, emmetropic subjects, saw the movie with the red unsharp, their eyes became longer. These are all effects in the 15 micrometer range. It's not big, but you can pick it up and it's significant as you see. But if you calculate the blue unsharp, then the eyes really get shorter because the choroid gets thicker. And these are the emmetropes on the left. But on the right, you get a problem because the myopes, as you can see, they don't respond. So it seems that this chromatic aberration detection is kind of compromised in the myopic eye. And it's clear there are now interesting questions. First, how can you show what is broken? A good idea would, for instance, that the blue channel in the myopic eye has less contrast sensitivity. And this year at ARVO, there were actually findings that this is the case, that the blue is not as contrast sensitive in a myopic eye. The second question is then, when does this happen? Is this there from the beginning, or does this happen when you get myopic? And all this needs to be studied in the future. But what we can say is now the chromatic aberration detection is broken in the myopic eye. We also did a long-term study with these movies. So the subjects had to come to the lab for 12 days. It's not really long-term. But what you can see on the left is choroidal thickness gets thicker and thicker when they watch these movies for 2 hours. Actually, it wasn't movies. They did regular work on the computer screen, only that the screen was filtered as I have shown on the right side. Either no filter, everything is sharp, but then the blue in focus and red in focus filter. And you can see that the choroid thickens over the 12 days and the axial lengths get accordingly shorter. So what we are missing here is a certainly long-term study in children by a by a computer work where you have filtered the blue and the red, or only the blue would be good enough for the moment. But this hasn't been done yet. So this was my part about which stimuli are important. And the second part now is, I think what is my time? Yeah, I still have time. Okay, sorry. Which retinal areas are important? And this is an unexpectedly interesting area because normally everybody would think emmetropization needs high acuity, so it's probably all controlled by the fovea. But you know now already that, excuse me, the fovea is not, it's not really playing. It's not really important. You can see the data now. I show you a little bit of historical data on peripheral refraction. The first really well visible study was Mileto 1982, who studied the refractive errors of people in the periphery, and he looked into myopes, emmetropes, and hyperopes. And what he found is that the hyperopes get more myopic in the periphery while the myopes get more hyperopic in the periphery. Certainly, all this is relative to the center refraction. And this is shown on the left. interestingly, when you assume that eye growth in a myopic eye is just that the eye becomes more elliptic, then you can calculate that this is what you would expect. And well, this is what it does. And on the right side, we have data. We did this also in our lab. We used the old power refractor to refract eyes over the visual field, and we have a grayscale encoded refractive error map there. And what we found also is that the hyperops in the bottom, they get more myopic relative to the center, and the myopes get more hyperopic. So this is looking like the eye really becomes elliptic in either the horizontal or vertical direction, depending whether it's myopic or hyperopic. But now imagine, wouldn't this stimulate myopia to grow and grow further? Because if the myopic eye gets more hyperopic in the periphery, this should stimulate more growth. So this doesn't seem to be a very nice thing because it makes the whole system even more unstable. And I must say it's not completely resolved whether this relative hyperopia in the myopic eye could be an additional stimulus for more growth. Now, we built a machine then. At the time, this was an easy funded project where we had a photorefractor that came in from the side, but then we moved a mirror in front of the eye as shown on the right top. And this mirror certainly made the eye refracted across different angles. And on the bottom left, you can see a subject sitting there, and this mirror moves and just goes across the visual field. And there you can see now the eye, how the photorefractor looks at it from different angles, and then you can immediately get a nice curve of what the refraction was in the horizontal visual field. Doing this, what Juan Tabanero, who's shown in the bottom right, what he found is that there is quite a big variability among different people. These are 10 subjects. The black line is when they did not accommodate, but you see the shape of the peripheral refraction is really quite variable. What you can also see, if these subjects accommodate 2 diopters, this is a red curve, and 4 diopters, this is a green one, the shape of the peripheral image plane is pretty much preserved. So accommodation shifts the whole image pretty coherently over the visual field. But there's a big variability. Okay. Then Pablo Attal and Bart Yecken, this was actually the PhD work of Bart Yecken in Pablo Attal's laboratory in 2012. They actually took a Hartmann check sensor, a wavefront sensor, and moved it in front of the eye. A lot of mechanical effort, as you can see on the left. And but they got certainly very extensive data. Basically, what this data at the end showed pretty much the same. If you have a hyperopic eye, you get more myopia relative to the center, and the other way around for a myopic eye. I show this only because this was a really impressive machine. I remember then when Bart Yecken showed it at ARVO in his talk, that everybody really got up and clapped. This was so impressive that he could scan with a Hartmann check sensor. This was a nice PhD work anyway. Pablo exported this to China, and these guys have measured many, many people. And the average statement we can make at the end that the peripheral refractive errors are lower than what we measure with photorefraction. And this is because the Hartmann check sensor takes all the higher order aberrations into account and provides you really the smallest point spread function as a measured variable, which we cannot do with a photorefractor. So there is still the peripheral refraction problem, but with a Hartmann check sensor, it gets less, just as a remark. So what we did in the lab then is we gave the chickens hemifield lenses, which means we defocused only the nasal or the temporal retina and see whether the eye can grow in both directions uh, in restricted parts of the visual field. And if you give a lens, you always get now a change in accommodation. So we could argue if accommodation takes care of this lens, then the retina doesn't see an error signal and probably doesn't deliver any signal to make different differences in eye growth. But this was not the case, and this is why this paper is called peripheral refractive errors induced by lenses despite accommodation. This was something which was very interesting for us. But what you can see, you get a tilt in this refractive error map over the visual field in either direction, which means again locally the retina picks up the error signal from the defocus and lets the eye grow differently. And this is not choroidal thickness. This was a 4-day experiment where you really get changes in eye growth. Yeah, this is an even more crazy experiment. There you see a chicken on the right that has a lens, and in the center of the lens is a hole. So there's zero power. The chick looks through this hole. Only the periphery of the visual field gets defocus. And what you can see on the left in these different refraction plots, if you have a full field plus lens, the chick gets about 7 diopters hyperopic, what you would expect. If you take a um, minus lens, you get myopia also as expected. But if you have a hole in the center of the visual field really stays emmetropic or normal sided. So it's only the periphery that grows differently. And basically, this gives you eye shapes, as you can see in the right top. Basically, the eye bulges out in only parts of the visual field, which is really impressive. And to keep the center in focus is, you can imagine how the growth control must be that the center stays in the right place when the periphery moves away. That's extremely impressive, actually. Yeah, well, all this wasn't yet ready to get into human applications, but it was in 2005 at ARVO where Li Fang Hang and Earl Smith's lab, they did a similar experiment then with the monkeys and gave them first occluders with a hole in the center. And these monkeys could look through this hole and had normal vision in the fovea, but the periphery got a degraded image. And what you can see, the controls had a refractive error. These are different animals with a standard deviation of, I would say, maybe it's about a half or a diopter, maybe, but the average is about 2 diopters of hyperopia, which is a small eye defect. But it's basically emmetropia for the monkey. But if you make the periphery myopic, you can see on average all these eyes moved into the myopic direction. Not all, as you can see. There are also some animals that didn't respond at all. And this is an interesting issue by itself. In the chick, we got a pretty consistent effect. Here we get a kind of effect, even though the fovea has normal vision. And basically, it's still interesting enough for the optical industry to apply this to humans. Yeah, I omit for time reasons the next two slides because I'm realizing time goes by. First, I would like to show again that the response in the periphery in these monkeys is very variable. I just made the point already, but here you can see it again. On the right graph, all animals were set to 0, and you got then only the change in refraction in the periphery, and there is more and more noise the further you go out, which is impressive and basically tells that you don't trigger the system the right way, or it shows that the refractor doesn't pick up all aberrations, and therefore, uh, yeah, it's not very convincing. Let's put this way. But nevertheless, in 2010, the first application came out with a Zeiss Myovision lens. You can see a picture on the top middle where this lens was sitting on the grating. And you can see basically this is a lens that causes, it acts like a reading glass. It gives you more plus in the periphery, but it goes in all directions with this reading glass activity. Now, I don't know, most of you are young anyway, but if you are not young and you got a reading glass, the worst is image distortion, which means you go down the stairs and you don't see the edge of the stairs on the right position. And in the beginning, you are at risk to fall. And this is a problem as soon as you get an increase in the refractive power of a lens, you introduce prismatic effects, and this moves the position in the visual field in a certain direction. And this is extremely disturbing. In the bottom, you see the interviews with the Chinese children who were wearing these glasses, and they say it took me a while until I could walk normally and all this stuff. This is exactly what you get when you are getting old and you get reading glasses. You have to train yourself with them. So it's a more difficult thing to get this to a large number of children, but I think it was done in China at least. And the second point is I told you before that in the myopic eye, there is a limited response to positive defocus. So at the end, may not be the best way to deal with myopia. And actually, these are the data that were first published in 2010. And you can see this effect is just almost nothing. That's really not worth it because the children are not happy with these lenses for a while and the effect is just small. So there were new ideas around, and some were probably, even though they were not kind of straightforward, they seem to work better. So an important progress was made by Dennis C. and Chio To, published in OPO, 2006. What they did, they gave the chickens lenses that had two focal planes, bifocal lenses basically, but they were alternating focus behind the retina, focus in front of the retina. So if you do this with the same amount of area and the lens, one segment goes behind, one goes in front, you wouldn't expect much to happen. And in fact, if they had a +10, -10 alternating lens with 50% uh, area covered on the lens, these chicks didn't really change much. So the retina realized the best focus is still in the middle. But now if you change the areas that is focusing behind or in front, then you can induce increasing amounts of myopia here, as you can see on the left. So this tells that the retina can really deal with multifocal images, which is not something that yeah, in a camera, when you have one pixel plane, it's hard to do early. And in the retina, this is striking that this can be done. I must say, I didn't fully yet have a model why this can work, a multifocal detection. Yeah, anyway, this was repeated in the monkey, you can see on the right. And also there it worked. You could make monkeys more hyperopic with a alternating zero power +3. So this is a nice approach, and actually it ended up also in the translational thing. It went to contact lenses, the so-called disc lens in children that work quite nicely, and certainly the MiSight lens maybe, which is also widely distributed, and there are now studies around over 6 years or even more. I don't know exactly. And they really at least seem to be consistent in inhibiting myopia, also not 100%, but maybe 60% or so. So the multifocal approach is much better than the peripheral plus defocus. Yeah, and then the next thing that was again Giotto, who was in the bus and watched, looked out of the window, and there were these plastic shields with the yellow arrow I show you there, just to get more shade into the bus. And he thought, why shouldn't we put many small plus lenses in a spectacle and see whether this can inhibit myopia? And he got Hoya apparently to build such lenses. I think Hoya will know when this happened and what happened. But anyway, these lenses are implementing many little +3.5 lenslets into the baseline of the lens, of the spectacle. And the hope was now that this causes a secondary focal plane in front of the retina that inhibits eye growth, which is a reasonable idea. And I thought when I heard this, oh, great, maybe we get better reading glasses for old people, because if you have a second myopic focal plane, why can't you read with it? And so I took one of my cameras that are kind of similar in the optics like a human eye. So 16 millimeter focal length and f number 5.4, which you see in the bottom left. And then I focus this camera on a 30 centimeter text. Certainly you can read it nicely, no problem. The camera is freed up as myopic, if you want to put it this way. Then I focus this camera at infinity, and the text remains at 30 centimeters. You can see it's now 3 diopters hyperopic, and you can't read anymore really. But then I added this treatment zone of the Hoya lens and was hoping that you can read now again. And I think you can get a slight improvement, as you can see on the right, and it's magnified a bit on the bottom. But it's not really nice if you want to do serious work. So it turns out that this multiple lenslet approach doesn't give you a really nice image on the retina. But the problem is, does the retina really need this? The retina doesn't see any forms or recognize any objects. It may be useful for the retina. So there's a lot of things to look at. And certainly, as soon as this Hoya lens appeared, I saw it first at the Birmingham Myopia Conference in 2017, already in 2019 in the Myopia Conference in Tokyo. There was Essilor with a similar approach, and Zeiss wasn't there yet, but it was just picked up by other companies, of course, because it looked like a great approach. And here I want only to make the point, if you take these different lenses and hold them in front of a camera that is focused on a text, and you can see this on the right, you can see the first box is just in focus. Second box is zero point 0.5 diopters out of focus, which you just turn the camera off a little bit. But now come these different lenslets from the companies, and you can see the general image degradation is similar to a zero point 0.5 diopter defocus. It's not really much. It's a small effect on the eye, and still it has an effect on myopia. And in the bottom, you see even another lens. These are these dot lenses that are just basically diffuse the periphery of the visual field, and they all inhibit myopia. It's very funny. But the image degradation is small, like zero point 0.5 diopter of defocus. In A now on the left side, you can see the effect size you get with these lenses that add positive or myopic defocus in the periphery. Typically, people add 3 plus or 2 plus, 2 diopters plus. So these are very different effect sizes. It's 6 times more what you get out of these other lenses, and they don't even work. So, or I shouldn't say generally, but my experience is that I couldn't see anything that convinced me. Yeah. Now, is this really an issue of myopic defocus with all these little lenslets? And then comes in very interesting editorial by Jess Guggenheim. This was 24, yeah. He summarized studies up to then, and there was one study from China where they took these DIMS lenses, defocus incorporated myopic segment lenses, but in the other direction, they basically put little negative lenses in there instead of positive. But still, myopia was inhibited. And I think this kills largely this argument that we are dealing with a secondary focal plane of myopic defocus that tells the retina that it should inhibit eye growth. It looks at a general degradation of the image in a certain way is already good enough to inhibit eye growth. And uh, there's a lot of speculation what exactly this is these days. Only I think we can safely say it's not myopic defocus. Now, let me get to the final point, which is really about which area in the retina is very responsive. And as you saw before, all these lenses that have peripheral image degradation or defocus, like Essilor, Hoya, or Zeiss, they have a clear zone in the center where the eye can see normally through. And there, if you have a myopic child, you certainly have to add full correction for their myopia so they can see normally through this central 8 millimeter zone. Now, if you calculate how big is this zone actually on the retina, this is not very difficult. At least the estimation is very simple. You need to know where the posterior nodal point is of the eye, and then this is the point where the chief rays cross, and they determine how big this spot is on the retina. And I briefly calculated roughly, so it's about 20 degrees that the retina gets a normal image with an 8 millimeter clear zone and a 15 millimeter lens distance. Now the question is, in this clear zone, apparently there cannot be any control of eye growth with these lenses because otherwise uh, you wouldn't get an effect on myopia. So there must be something, a different area that is important. Yeah, and I briefly would like to mention also there was an electroretinogram study which was very nice coming from Panorgas from this is also from Boston, yeah, from Boston actually, New England College. What they did, they had a so-called dead leaf pattern which you see on the left. This flips over in contrast and you record ERGs and you get these curves that you see in the middle. But now what they did, they low-pass filtered parts of this area, so the retina did no longer get a sharp image, and this is shown in the bottom. In this way, they could find out in the ERG which area of the retina is really responding to a low-pass filter or poor image quality. And what they found, it's mostly the area between 6 and 10 degrees that is responsive. And 6 and 10, 12 degrees is about in the range where we have the clear zones because this is a diameter and we have the radius. And so what we then did, we wanted to know exactly which area is responsive to defocus. And these experiments were done by Barbara again, which you see, whom you see in the top. And I wrote the software to really patch parts of the retina in a movie that the people were watching. What you have to do then, you have an eye tracker certainly to measures where you are looking at, but then you have to take the eye tracker output and feed it into the software that shows the movie. And this was a little bit an effort because you need to get this in real time and you would like to patch different areas. But finally, we got it going, and people were now watching the movies while parts of their visual field are covered. I wanted to show you on the right, on the left, this little movie. You can only measure one eye at a time reasonably well, so it's important that you argue that the other eye looks at the same spot on the retina. So you have to track only one. And what you can see here is I'm fixating a yellow spot here, and this is what my eyes are doing. The spot size is about 10 minutes of arc, and you can see the eyes are really dancing around each other. And these are the so-called fixational eye movements, as you know. But it's important to know that both eyes look at the same spot. Otherwise, you would see double images. So what Barbara did first is check whether left and right eyes were always looking at the same spot in the movie. And this was done with a binocular eye tracker that we programmed, which is shown on the left. Yeah, so it shows the experiment. The right eye got a plus lens, so we are triggering positive defocus induced choroidal thickening. The other eye was used for eye tracking. And now this is the measurement. It's actually in the dark, but for the movie, I switched the lights on. So Barbara now has a fovea patched here on the screen. This is a 6-degree spot that takes the fovea and the perifovea and knocks it out. Basically, you have no information other than gray. And you can see how I always like to watch how what the eyes are doing, how the brain already tells you next you should look there. This is interesting because it's always a little bit ahead of the action in the movie. This is quite impressive. And the next thing now is really these are the different things that we had. I don't know whether in real time on your displays this is in real time or Stardust. I don't know really. But you can see on the left top, you patch the fovea, then we patch the 12 to whatever degrees. And so you could patch everything in the retina. And the good thing is at the end what the results were. So you give first full field defocus with the plus lens. You see on the left, the eye gets shorter by about 10 micrometers after 40 minutes. Next thing, you patch the fovea. Now in green, the curve, you can see exactly the same. It didn't matter whether the fovea is patched or not. Next thing is you cover the area between 3 and 9 degrees eccentrically around the fovea. And you can see the eye does no longer respond to the plus lens. So this is the area that is most sensitive to defocus here. And finally, Barbara did a number of combinations of different stimuli, and although the one in the bottom is not very effective, but the most striking is on this experiment here. If you just only stimulate the ring between 6 and 10 degrees around the fovea, you get almost the same effect as if you have the full field stimulated. So this is where the business seems to happen. And now you can see if you have these lenses with an 8 millimeter clear zone, it's touching about the area that most sensitive, but it could be a little bit better by making this treatment-free zone a little bit smaller. That's what we thought from our experiment. And finally, what happens in this area? This is certainly interesting. And yeah, here on the left, you can see a curve of how the cones are distributed across the retina. In the foveal center, you get about 150,000 per millimeter, but they fall off very quickly. At 10 degrees already, you have only 10% of cones left over. The rods have a peak at about 15 to 20 degrees off. So what happens exactly at this red bars? This is the area where the defocus sensitivity is. And actually, if you look at the S cones, blue cones, the ratio of blue cones to the LM cones has a kind of a peak in this area. And since we still assume chromatic aberration is the key player here, certainly it would be great to have a high blue cone acuity. And I think this is probably the reason why this is the most sensitive area. The other thing I would like to make, point that I would like to make, you get all this funny arrangement only due to the fovea. Animals who don't have a fovea probably don't have this. It's only because I had to make a compromise here to put the eye growth control out of the fovea because the high spatial frequencies that the fovea uses for vision, they are not useful for emmetropization. You need a mid spatial frequency area which gives you a reasonable error signal over a wide range of defocus. And this is why I think the sensitive area was placed out of the fovea a little bit, and we can now measure where it was. Yeah, this is Christine Kurstius. She mapped out all these S cones and LM cones very nicely, and this is where we came up with this 7.6% of S cone density in this area. And I'm now through it. I think so. You saw the emmetropic retina is perfect, can generate a growth stimulating and growth inhibiting signal. Myopic retina has at least problems to detect positive defocus and generate inhibiting signals for eye growth. When it happens, is a good thing to study in the future. Experiments explain why myopia does not inhibit itself. Yeah, if the inhibitory pathway is not acting, then you can't inhibit anything. And patching the fovea shows that the most responsive area in our basal experiments was around 6 to 10 degrees away from the foveal center. And that's what I wanted to say. I'm almost through. Thank you very much for listening.
Thank you very much, Frank. Attendees, we have a few minutes. If you have any questions, can you please put it in the Q&A box so that Frank and I can have a look at them, and then we'll try and answer those questions as much as we can. I want to again thank Hoya for supporting us for this webinar and for Frank for taking the time and for rearranging and still making it to come and join us again. The first question is in, Frank. It says for the short-term myopia axial length study, were they extrapolated axial length from the choroidal thickening or from the axial length measurement?
Yeah, also in Basel, we only had the lens star available. Actually, that's not true. In the long-term experiment, Barbara also went to the clinics and got a OCT. And this is also published that most of the effect from the axial length comes from choroidal thickening. But it wasn't 100% match, I must say. But I don't know how precisely thickness of the choroid really can be measured because of the refractive indices along the way. And this is a different question. But basically, it's all coming from the choroid, I believe. In 30 minutes, you wouldn't get eye growth changes.
Thank you. Mark Willimos says, wonderful talk. And we've got another question. Uh, if the answer for myopia spectacles is actually contrast, why is it that the dot lens don't perform as well as the other defocus ones?
That's an interesting point. I saw a paper from the Zeiss Vision Lab where they compared actually the special features of these dot lenses, and they are not equal to, for instance, Bangerter foils. Bangerter foils, at least, are certainly not the best way to go because they are known to cause myopia. But these dot lenses have a special structure which causes a slightly different stimulation or image degradation. But at the end, it's really we have to exactly define what image degradation is efficient to inhibit eye growth. But this is a dangerous business in a way because you can flip over to deprivation myopia. And if you do a children's study without knowing exactly what they are doing, I think this can be risky. So we still need to understand exactly what image degradation is efficient. I think what is very important is to find out what the on and off pathways are doing in all these cases because stimulation of the on pathway generates more dopamine in the retina and inhibits eye growth, as you may know anyway. So it's important to define the stimuli very, very well, I think. I hope this answers your question. But Mark, you know more about it maybe than me, so I just was reading into speaking into the air, I guess.
We have a few other comments to say thank you for the talk. Chris Hull has asked the question, is there any indication where the inhibition feedback loop is breaking down in myopia? Do you think it's optical, retinal, or neural?
I don't think it's optical because if you give an emmetropic person a plus lens, you get this inhibitory effect. So the optics is basically why should the myopic eye no longer present any myopic defocus? This doesn't not to make much sense. So genetic it can't be because, as you know, the children who are not reading a lot are getting less myopic. So it's not the genetics by itself. At the end, it must be a switch off either in the ratio of on and off channels, but then you still have the question, why does this happen? Does it happen when you are reading too much and you disturb the balance between on and off channels? Yeah, thinking about it, I think I would expect that there is a problem somewhere.
Okay. We have another question. Do you think by using peripheral defocus lenses for prolonged duration for myopia control will have negative effect on peripheral visual field?
Yeah, this is a half diopter equivalent image degradation, which I don't think can be much problem because our image quality in the periphery isn't so good anyway. So depth of focus for half a diopter is in the periphery is probably not detectable, I would think. So I can't imagine that this is a problem. You can hardly measure contrast adaptation changes with these lenses, and as soon as the image is degraded, you get contrast adaptation normally which you don't see. So I don't think it's really a specific effect on the emmetropization mechanism, not on vision.
Okay. Um, Mark Bullum has added to the question about dot lenses. The results from China suggest that dot lenses may be as effective as other designs.
Yeah.
Essilo and Paris authors presented a unifying model at Arvo. So,
Yeah, I wasn't at ARVO to see this. I read the abstracts, but I didn't see this particular study. Was this a talk or a poster? Do you know whether it
I,
doesn't matter? We shouldn't discuss directly. Yeah, yeah. Okay.
um, final question, if you're happy with this, I'm not sure that we have the answer, but what is your opinion on various light treatments for myopia, specifically the blue and amber light now?
Yeah, I think this is all. This is enough for another talk, at least of this length, because there's so much about it. I think the problem here is again that if you change the spectrum a little bit, you switch from the inhibition to the stimulation. And so it's quite a bit of work still necessary until you can directly apply it. I just saw a paper again by Lisa Austrian about reading in blue light, which also makes now the choroid thicker, which is nice, but it all doesn't fit yet together, in monkeys and tree shows, the red is so powerful, and now why should be the blue also so powerful? I only can say in the chicken, which responds really to chromatic aberration, you get a shorter eye in the blue and a long eye in the red, which is just detecting chromatic aberration. But in humans, this is messed up, and I think there's still a lot to think about.
Well, that's another discussion, as you rightly say, Frank, and
Yeah.
one of our future webinars, hopefully, that we can look at all of these discussions as well. Um, Thank you, everyone, for attending. Thank you, Frank. Thank you for the questions, for the interesting discussions. Just to tell you all that those who remained on the webinar until the end will receive a certificate of attendance in the next 2 weeks. It's not going to be immediately, but in the next 2 weeks, you'll get a certificate if you want to apply to your countries on CPD points as well. It's thank you to Hoya. The recording of this webinar again will be shared with Hoya so they can put it on their educational platform channel, and it will be in the European Academy's member section as well for those who are members to access the recording from this webinar. But thank you very much for a wonderful talk, Frank, and thank you very much everyone for attending as well.
Thank you.
And hopefully we see everyone next year in Bern for our annual conference. And those who are not members of the European Academy and want the recording for this, you can join to be our members for €110. for the year and join exciting webinars like this. So
Thank you.
thank you, everyone. Thank you
Thank
very
you.
much.
Thank you. Bye.
Bye.
Mm.